Alright, awesome astronomy students, we're going to practice using Dr. Wiles' math shortcut. As you know, all the math in our astronomy class is going to be able to be completed using the two sentences here. Both on top do the same, one on the top and the other on the bottom, they do the opposite. So we're going to practice this, and this video, along with the other documents available about Dr. Wiles' math shortcut, should help you be successful doing any math that we run into in astronomy. So let's start using an equation. We'll use Newton's universal law of gravity. It says that the force of gravity is equal to the gravitational constant G times the mass of one object times the mass of the other object. And then it's divided by the distance between the two objects squared. So force is equal to gravitational constant times the mass of one object times the mass of the other object divided by the distance between the two objects squared. And let's imagine that you get a problem and the mass is going to change. What you want to do is point an arrow at mass here. And let's just say in this case that I give you a mass that is bigger. So in this problem, somehow a mass becomes bigger, okay? And what we're after is how changing the mass affects the force, okay? So if the mass gets bigger, does the force get bigger or smaller? All right, when you point your arrow at the force, you can then go look at the mass. It is on top. It's in the numerator. It is above the dividing line. Force over here on the other side of the equal sign is also in the numerator. It's on top. It's not below a dividing line. And here it says both on top, they do the same thing. So if the mass gets bigger, the force absolutely must get bigger. Now let's suppose we stick some numbers in. Let's suppose I make the mass 2 times bigger. Now looking at the masses here, there's no squares or cubes or square roots or any kind of exponent or power whatsoever anywhere on them. And if there's no exponent or power, then if the mass gets 2 times bigger, the force also has to get exactly 2 times bigger. And you're done with that problem. You've got a final answer of it gets 2 times bigger. Okay. Let's use that same equation and look at it again. So I'm again going to write force is equal to gravitational constant times the mass of one object times the mass of the other object divided by the distance between them squared. So same equation, universal law of gravity that Newton figured out. Now, however, let's make the distance bigger. So instead of making a mass bigger, we're making the distance bigger. Well, how does that affect the force? We're looking for whether it will make the force bigger or smaller. So now you can point an arrow at force, and you look at the distance. It's underneath the dividing line. It's on the bottom. Fancy term for that is in the denominator. Force is still over here on the other side of the equal sign on top. So now we have one on top and the other on the bottom. They must do the opposite. So if the distance gets bigger, the force must get smaller. Well, let's put some numbers in here too. Let's just suppose I said some distance gets 2 times bigger. Well, this one's just a tiny bit more complicated because the distance itself gets 2 times bigger. But the force is affected by the distance squared. So force is affected by the distance squared, which means that when I want to figure out the number for the force, I have to put the 2 here and then square it. And 2 times 2 is 4, and so the force will be 4 times smaller. Okay. Well, let's just try this with another equation. Let's use the one that has wavelength is equal to the speed of light divided by frequency. Wavelength is equal to speed of light divided by frequency. And let's just suppose I gave you some kind of problem where I said the force is going to be made smaller. Okay, sorry, not the force, the frequency. Little f for frequency, c for the speed of light, which is a constant, and then the symbol, which we'll learn in chapter 5, is for wavelength. All right, frequency gets smaller. What happens to the wavelength? Well, let's point our arrow and figure it out. Notice that frequency is underneath the dividing line on the bottom over here, and on this side of the equal sign, the wavelength is on top. It's not underneath the dividing line. So again, we have one on the top and the other on the bottom. They do the opposite. So if the frequency gets smaller, the wavelength must get bigger. And we can put a number in here too. Let's just make something up and say it gets 17 times smaller. So if the frequency gets 17 times smaller, how many times bigger will the wavelength get? Well, again, no squares or cubes or square roots or anything like that here. And so the answer is just 17 times bigger. Now you're done with that problem as well. Let's try one more. Let us look at the equation that says the velocity of a galaxy in expanding space is equal to the Hubble constant times the distance away from us that galaxy is. So velocity is equal to the Hubble constant times distance. And now, again, just make something up. Let's suppose I make this d smaller. So this distance of a galaxy away from us gets smaller. Notice that over here it's on top. It's not under dividing line. And velocity over on the other side of the equal sign, same deal. It's on the top, not under dividing line. So when you point your arrow to see what happens to the velocity, we've got both of them on top. They must do the same thing. So if the distance gets smaller, the velocity must get smaller. And now again, let me stick some numbers in. Let's suppose I make this 17 times smaller. Just making some numbers up. So if I make the distance 17 times smaller, again, notice for this one, no squares or cubes or square roots on this distance. There was for the distance with the gravity law, but not for this one. And with no kind of exponents up here, then that velocity is just 17 times smaller. And there it is. Practice doing several different equations using Dr. Wiles' math shortcut. I hope this helps you be successful in our class.